Physicists have developed a number of mental pictures of what's happening, but there's no agreement about which one's right.
There's something called the collapse interpretation. The idea is that there's only a wave that passes through the slits, and then the wave, when it arrives at the screen, it collapses, so it's only detected in one of the many possible places it can be detected at the screen.
It seems to behave as a wave in between the source and detector, so it can go around these barriers and go both ways through the slits.
The pilot wave interpretation says that electrons are real particles, like tiny, tiny tennis balls, guided by an unseen wave.
In this case, you can explain why the particle is only detected in one place behind the slits, because there's only one particle.
It's this pilot wave that tells the electron what to do. So the pilot wave mysteriously knows about everything, where everything is in the universe, and it feels whether or not there's a one slit or two slits, or one slit open or the other slit open. And it can somehow tell the electron about this and move it around and get it to go different places.
If wave-guided particles aren't your thing, how about parallel universes? The many worlds interpretation explains the double slit experiment by saying that parallel universes are being created all the time.
So in quantum mechanics, we have superposition of different states, and the many-world interpretation says that all these different superposition of states are equally real.
The world literally splits into many copies, and so we only see one thing happening, but there are people in another parallel world who see another thing happening.
While some researchers attempt to construct mental images of the quantum world, others think this world can't be pictured. The Copenhagen interpretation says that we should focus only on the results of measurements in quantum experiments.
When an experimenter enters a lab and interacts with a quantum mechanical system, the Copenhagen interpretation says don't ignore that interaction. It's a crucial piece of what's happening.
It's very powerful to restrict yourself to questions about what we can see. It's very powerful to restrict yourself to questions about what we actually do, because that teaches you to think about the experiment in a very honest way, in a way that appeals directly to the experiment itself without invoking extra theoretical ideas.
In the double slit experiment with electrons or with photons or with buckyballs or anything, the question is what happens between the source, the double slit and the screen. John Archibald Wheeler, famous American physicist, said, "This is just a smoky dragon," meaning that we cannot talk about it. We can mathematically describe it, but it is impossible to make a picture.
I think none of these philosophical discussions bear fruit. The only thing that bears fruit are the calculations.
There's no consensus about which interpretation is right, but they all predict the same results for all experiments.
We really do know what's going on at the subatomic level. We have a complete and accurate mathematical description of what happens.
That mathematical description is something everyone agrees on. It allows us to make incredibly accurate predictions, and that's very useful.
Something that people didn't anticipate is that if you have a weird version of reality, then you can make that weird version of reality do some work for you.
Do some work for you? That's weird.
How can quantum work for us if we don't even know what's going on?
We know what's happening. We just don't know why.
If we can't measure a quantum object without disturbing it, what can we possibly make?
Plenty.
Quantum physics is invading everyday life, even if we're not aware of it. And so as the world becomes increasingly more technology-oriented, we're just going to see a world that is increasingly quantum physics-oriented.
Many technologies take advantage of the wave behavior of electrons. One of them is the electron microscope. An electron with a large momentum has a wavelength much smaller than visible light, so scientists use electron microscopes to resolve objects down to the level of individual atoms. We can look at strands of DNA, examine viruses, and design nanotechnologies. The particle nature of light is at the heart of a range of everyday technologies. Traffic lights, solar panels, barcode scanners, and remote controls are all devices that incorporate quantum effects related to photons.
Inside modern devices for information processing, like CD players, cellular phone, computers, there are, at the brain itself, there's an element called a transistor. And the transistor would not work today if we would not have the laws of quantum mechanics.
We can control the flow of electricity. We can amplify it, we can turn it off, we can turn it on. Our ability to turn things on and off, control the flow, gave us logic gates. Those logic gates, when we were able to replicate them on a mass scale through commercialization of that discovery, led to integrated circuits led to computers, computers led to the information age and the internet.
If you do not think quantum mechanics is important and you do not like quantum mechanics, you can choose to live your life without it. Please get rid of your cell phone, your iPod, your computer, all electronic equipment, and then you can live your life without quantum mechanics.
I had no idea my phone was quantum.
No one knew the range of technologies possible when the theories were first presented 100 years ago. But our knowledge developed over decades.
Quantum mechanics has revolutionized the way we live our life. The development of the technology and applications enables more science to be done. As more science is done, more technology and more applications are developed.
At the Institute for Quantum Computing in Waterloo, Ontario, researchers are developing a range of new quantum technologies. Quantum cryptography takes advantage of the concept of measurement disturbance. It's the basis of ultra-secure secret codes that are starting to be used by banks and governments to safeguard highly sensitive information.
In quantum physics, when you make a measurement, it doesn't tell you everything about the system you're looking at. And further, just by looking at the system, you change it. In cryptography, we can use this to detect eavesdroppers. So not only can an eavesdropper not get all the information about a system, but will inevitably change the signal and can be detected. So it's quite clever, actually.
Researchers are also using quantum physics to build a new breed of ultra-powerful computers.
So the idea of a quantum computer is, suppose you built a computer out of individual atoms or other very small objects that were behaving quantum mechanically. Then instead of just having one number in its memory and doing computations on that one number to get an answer, it could have, in some sense, many numbers at the same time and do computations on all of them. And so consequently could solve some problems much faster than any regular computer.
In the case of quantum computing and quantum cryptography, we go much deeper in the quantum world, much kind of places where we don't only put our big toe in the ocean of the quantum world, but really go and swim in it.
And what's really exciting is that we can't even imagine the kinds of discoveries that our future physicists are going to make.